Hello, welcome to lesson number 4 in radioactivity, the Juma. So, in this lesson, we're going to look at the decay series, differences between nuclear fusion, nuclear fission, and also we can look at some dangers of radioactivity and application. Can allow not to do that, we can put it in lesson number 5. So, what is a decay series? We have defined this, the introduction among the terms that we defined. So we say that a decay series is a sequential and continuous disintegration of unstable nuclides until a stable nuclide is formed. So it is a process that is continuous, where we have one nuclide, which I had illustrated in the previous the introduction. For example, let's say we have an element A. If element A is unstable, then it will emit some particles and energy to form element B, or nuclide A forms nuclide B. And if B formed is not stable, it will also emit some particles and energy. It will undergo disintegration to form C. If C is not stable, it will undergo disintegration to form D. If D is not stable, it will form E. If E is not stable, it will like that. So this process is continuous until a stable nuclide is formed. So let's look at one of the series. We have the theorem series, we have the Radium-235 series. So we have different elements starting from a particular element, then disintegrates until gives you a stable nuclide. So let's just look at one of them, and that will be the theorem decay series. So let me just project this on your screen so that we discuss as you look at it. Okay, so over here we have what we call theorem series, that is starting with an element called theorem. So you can see from now, starting from this first element theorem 232, now it loses this particle there, that is what we call an alpha. And if you can remember, we say the effect of losing alpha is that, or emitting alpha, is that the mass number reduces by 4, atomic number by 2. So you can see that is why the mass number is reduced from 232 to 228, while the atomic number is reduced from 90 to 88, then forming radium. Radium loses or emits beta particle, and the effect of beta, we say that beta has no effect on mass number, but it increases the atomic number by 1. So you can see the mass number has remained the same, 228, and then the atomic number is increased from 88 to 89, then forming actinium. Now actinium emits beta particle. As we have said, beta has no effect on mass number, so you can see the mass number 228 still remains 228, but the atomic number has increased from 89 to 90, forming back theorem 228. So you see this was theorem 232, forming another isotope of theorem, that is theorem 228. And then theorem emits an alpha particle, you can see that, and alpha, the effect, mass number reduces by 4, so you can see from 228 to 222, then the atomic number by 2, so you can see from 90 to 88, forming again radium. Now another isotope of radium, because look at this, radium is 224, but the other radium was 288, but you can see the atomic number is the same, 88, but the mass number is different. So it's another isotope of radium. Then radium now emits an alpha particle. You can see there, that is the sign for alpha. Alpha, the mass number will reduce by 4 from 224 to 220. Atomic number by 2 from 88 to 86, forming radon. That emits an X particle there, so there you have been asked to, or it has been left for you to identify which particle is that. Now you can identify that, though there is a mistake here. This should be 84, not 24. This is 84 and not 24. So in this case, from 220 to 216, that is an alpha. So this means particle X is alpha because the mass number is reduced by 4, atomic number by 2, from 86 to 84. So this is 84, not 24. And then from there, another alpha lost, 216 minus 4, 112. 84 minus 2, you get 82. Then forming lead. Then lead loses or emits beta, forming bismuth. Bismuth, you can see the mass number there has reduced. The mass number remains the same because when beta is emitted, there is no effect on the mass number. So you can see 212, but the atomic number has increased by 1 from 82 to 83. Then bismuth forms titanium. So from there, you can see the mass number, because of emitting alpha, the mass number is reduced from 212 to 208, reducing by 4, atomic number reducing by 2 from 83 to 81. And then from titanium, beta particle is emitted, and then forming lead again, lead 208. This other lead was lead 212, so this is another isotope of lead. The atomic number the same, 82, but the mass number 212, this is 208. So you can see from titanium to lead, when beta is emitted, no effect on mass number. The mass number remains 208, but the atomic number increases by 1 from 81 to 82. So that's an example of a decay series where an isotope, a nuclide, emits a particle, either beta or alpha, with energy. So you can see in this entire series, gamma have not been shown anywhere. So usually on decay series and in most even equations, gamma are not indicated. The reason is because gamma is not a particle. It is released in form of energy. So in this entire process, a lot of energy is liberated. So most of that energy liberated in form of gamma rays. So we said gamma rays are not particles. They are rays. They are emitted as energy. So that's why they are not indicated on that series. So let's consider nuclear fission and fission, the difference between the two. So these are nuclear processes. So nuclear fission is the splitting process of a heavy nuclide when bombarded with a fast-moving energy particle, such as a neutron. So it is the splitting process of a heavy nuclide when bombarded by a fast-moving neutron. Now an example is here, uranium-235. When bombarded with a neutron, it splits, giving 2 daughter nuclides, that is barium and krypton. The process, 3 other neutrons are liberated and energy. The energy liberated can be harnessed and be converted to other forms of energy. Now consider this. So in this equation is balanced, not in terms of the atoms, because you can see this is uranium, barium, krypton. As I said, with the nuclear equations, we don't balance the number of atoms, but we balance the atomic numbers. So the masses, the numbers at the bottom and the numbers at the top, the mass number. So we have here 235. So like on this side of the reactant, so we have 235 plus 1, that gives us a total of 236. While on this side, if you take 141 plus 92, then 3 times 1, that will be 3. So here you have 141 plus 92 plus 3 times 1. So this will give us a total of the same as this one, 236. Then here 92 plus 0, that will be 92. Then 56 plus 36 plus 3 times 0 is 0. So if you add this, this will also give us 92. So during balancing, this is what we do. So in this case, we consider this as balanced. Now, usually, a lot of heat energy is produced in this reaction due to the fact that, okay, here I have explained that the masses are the same. But if we just disregard the neutrons, only consider the masses of the elements. So consider these ones, like now these ones are the follows. Now if we ignore, let's say this one, the particles emitted. Now if you take this mass here, this would be 235. If you take this plus this would be 233. Now there is some slight difference here. This would be 233. So there's slight difference in mass, 235, 233. Here the atomic number remains 92. But here, now this difference in mass, as small as it might be, this is the explanation why there is huge amount of energy liberated. As we looked at the differences between chemical and nuclear reactions at the introduction, we said that in nuclear reactions, huge amounts of energy are liberated, and that is explained in terms of the differences in mass. So just slight difference in mass between the mass of the reactors and the products accounts for that huge amount of energy. And as I've said, this amount of energy that is liberated can be converted to other forms of energy. For example, electrical energy. Then electrical energy can be supplied to consumers, to factories, industries. Then there will be other main uses that can result from the electrical energy. But also take note, this amount of energy, if misused, can be very destructive, particularly if it is used as a nuclear weapon. If it is weaponized, then it can destroy a lot of property and lives. So this has to be taken with a lot of care. Then another thing is this. Now, so if we consider now, here there was only one neutron hitting this nuclei. Here there are three. And these three nuclei, that the neutrons that have been released, they are also released at a very high velocity. Now, if they meet another heavy nuclei, they will hit that nuclei and making it to split to other daughter nuclei, releasing energy, liberating three more nuclei. Now, this type of reaction leads to what we call chain reaction. Chain reaction. So, in which you have one neutron, then this one. So, this one has given rise to three other neutrons. These three. Now, each of these will hit another heavy nuclei, leading to other three nuclei, neutrons. Same to this. And each of these again is it is able to hit another heavy nuclei and also resolve. Now this is now what we call the chain reaction. So this reaction, nuclear reactions, they have to be controlled. Otherwise, it might result to chain reaction, get out of control, and it can be very, very destructive. Nuclear fusion. Nuclear fusion is the process in which two light nuclei, so we say the plural of a nucleus is a nuclei, so in which to form, they collide to form a heavy, in fact should be nucleus. So the two join, so here you have them joining, here you have splitting process. So fission, you have from fission, so fission is for splitting, fusion is for uniting, so U for uniting, fusion, they unite, they join, they unite, to form a heavy nucleus when they collide at a high velocity. So in this case, light nuclei are made to collide at a very high velocity. They stick together, forming a heavy nuclide. For example, here. So hydrogen has three isotopes: hydrogen 1, hydrogen 2, and hydrogen 3. So for example, in this case, hydrogen 2 and hydrogen 3 nuclei, they are very light. So the nucleus of this hydrogen 2 and the nucleus of hydrogen 3 can be projected from the opposite direction so that they meet at a very high velocity, and then when they meet, they are accelerated and they meet at a very high velocity, they collide. So when they collide, then they form another nucleus, in this case helium. So you can say this is heavier than either of these two. And in this case, again, balancing will be the same. 1 plus 1 is 2. Here we have 2 plus 0 is 2. Then 3 plus 2 is 5. 4 plus 1 is 5. And then similarly, just like what we have done there, if we just omit the neutron there as a fall-off particle there. Now, the amount of energy that, if you consider now just the element, the hydrogen and helium, this is 5 and this is 4. So the difference in mass between the elements is what accounts also for the huge amount of energy that is liberated. So one similarity between fusion and fission is that in both processes, huge amounts of energy is liberated. In each case, a neutron is emitted. In each case, it results into chain reaction, because this neutron now can start off this type of reaction as we have seen in nuclear fusion. So let me just project those differences for those who may want to take down the notes. I've prepared the notes for that. So let me just project those differences on the screen and even the similarities, and then we conclude by looking at the applications of radioactivity as well as some dangers, and that will mark the end of our topic, that is radioactivity. So the similarities between nuclear fission and nuclear fissions are the following. So in both cases, large amount of energy is released. Both cases result in chain reactions. In both cases, subatomic particles such as neutrons accompany the process. The energy released can be harnessed and converted to other forms of energy or useful energy such as electricity in both cases. And then in both cases, large amounts of energy produced in the reactions can be very destructive if misused, such as in nuclear warfare, as I had discussed. Now let's consider the differences between nuclear fusion and nuclear fission. So the differences between nuclear fusion and fission, just two. In fusion, the process occurs in nuclei of heavy elements or heavy nuclides, while fission, the process occurs in the nuclei of light elements, those that have very small mass. In nuclear fission, the process involves splitting of the heavy nuclei, forming lighter ones, while in fusion, the process involves joining of lighter nuclei to form a heavy nucleus. Now, finally, let's consider the applications of radioactivity and the dangers. So, applications of radioactivity. So, the uses of radioactive isotopes are very many. So the first area that we are going to consider will be under medical application, and the following are the applications in the field of medicine. Okay, radioactivity is used to destroy cancerous tissues when a patient is exposed to correct dosage of radiation from radioactive nuclide. Sterilization of surgical instruments using gamma radiation. Radioactive iodine, iodine 31, is used in patients with defective thyroid to enable doctors to follow the path of iodine through the body. and finally for providing power in hard pace setters. Application in agriculture. So the following are the applications. Radioactivity is applied in agriculture. First, in the monitoring of photosynthesis and related process, such as carbon dioxide containing radioactive carbon-14 is used, and the path of this carbon can be traced during the growth of the plant. Also, in monitoring the absorption of phosphate fertilizers, radioactive phosphorus can be used to determine the rate of absorption of the fertilizers. And then we have other uses, or what we usually just term as the industrial uses or industrial applications. So in industries, we have preservation of food by exposing microorganisms to gamma radiations, which kills them. Gauging of the thickness of thin metal and paper sheets, measuring the level of food in canned and packed food, determining the age of archaeological materials in fossils from carbon-14 dating, and then detecting leakages in underground water or oil pipes without digging them out, and finally manufacture of nuclear weapon and atomic bombs. So finally, let's look at the dangers of radioactivity and pollution. Radioactive materials can pollute the environment in a number of ways. So let's see these ways. So one way in which radioactive materials can pose danger and pollution is during the disposal of nuclear waste. For example, the lead blocks used for burying materials corrode after a long period of time, emitting radiations before a stable isotope is formed. Also, during testing of nuclear weapons in oceans also causes the pollution, since plants and animals may take in radioactive materials in the water. Then finally, during destructions such as the mass destruction of Hiroshima and Nagasaki in Japan during the First World War, a lot of destruction was left behind long after the war was gone, because some of the materials that were used in manufacture of that bomb, they continued to emit radioactive particles into the atmosphere, and these materials affected people for a very, very long time. And they affected, like for example, the body cells, or what we call the somatic cells. So for example, somatic cells, these are the effects to the body which show within an individual's lifetime and appear in different manifestations. For example, e.g. skin damage, eye cataracts, damage of the liver, spleen, thyroid gland, reduced fertility, leukemia, and carcinoma, that is uncontrolled growth of cancerous tissues. These radioactive materials can also affect genetic cells. So genetic cells, these ones genetic effect will involve slight mutation in the DNA of the cell. It can lead to problems as chronic heart diseases. Genetic damage can appear in offsprings or subsequent generation. Radiation affects reproductions with the gametes produced containing mutated chromosomes, thus causing hereditary defects in the offsprings. For example, the children sharing a heart, or a child with a goat's heart, and so forth. So those are some of the dangers of radioactivity. Thus, it is important to control pollution by radioactivity. For example, proper use, storage, and disposal of radioactive materials, regular check of equipment which emit radiations, and promote an environment which is safe, secure, and peaceful. Use of nuclear technologies and the use of the nuclear technologies in the world, for example, Let's use the nuclear technology to produce useful energy, not for war and such, which affects human life and other organisms. So that will mark the end of our topic, radioactivity. I wish you all the best. Look forward to your cooperation. I am doing my part. I hope you are also going to do your part. I wish you all the best. For those who are accessing these videos through the YouTube, please don't forget to subscribe, press the notification bell, and share with your friends, notify them of the same, share with them, and God bless you.